Welcome to our Economics of Innovation course. Today I'm going to present to you the Dasgupta Stiglitz model. We briefly discussed it already last week. It's chapter 3, industrial structure and the volume of R&D, and goes back, as I mentioned already, to the paper by Dasgupta and Stiglitz 1980. Until now, in the arrow model, we only considered a case where only one of the firms in the industry active could implement some R&D project or could innovate. Right now, we are turning to industries which are more like the automotive industries, where all of the firms in the industries which are active invest in R&D. And what would be better than a Cournot model to deal with that? And that's actually what Dasgupta and Stiglitz did in the 1980s. So we looked into R&D competition, and where all firms in an industry could and actually did spend on R&D. I already introduced to you briefly how these R&D expenditure affects cost. It's actually again a process innovation. I gave you briefly how this functional form looked like actually. So if you want to start or if you want to produce a car, you have to invest in R&D. So you have to invest a certain level of X in order to get a certain level of variable production cost. That's what we have, and we introduced that, and what you saw was that costs are decreasing R&D, but at a diminishing rate. That's what we have, and the total cost you have then is this expression. So we can move on to explain the model in more detail. First of all, we look into the Cournot model, and we consider the case where we have a fixed number of firms due to some kind of barriers to entry. The model is hopefully rather straightforward, even though it gives some ugly expressions to you. Okay, Cournot model. First of all, we always need a demand function, or as it's Cournot, we put it in terms of the price variable, so it's the inverse demand function. We make some simplifying assumption, that is, we assume specific functional forms. The specific functional form is isoelastic. Here one looks again ugly, where sigma is something like a market size and epsilon is demand elasticities. If we put it like this, with sigma times q raised to the power of minus 1 over epsilon, the result we get, I just plotted this if I find it, for a specific function. Here I show it to you in OneNote. Hopefully you can see it. Here's just the function, how it looks like. This would be P, oops, if I can draw here, P is sigma is, I assumed it 100, I don't know whether you can read it, 100 times Q raised to the power of minus 1 over, what data? Actually, I used 2, so the elasticity would be 2 in this case. That's what you see how this function looks like. I showed you the functional form of this isoelastic demand curve, and also just a minute ago and also last week, this functional form of this R&D cost function, in a sense. So X is our expenditure, C is resulting marginal or variable unit production cost. N firms are active. That's just our assumption that we have a given number of firms and barrier to entry. In the second step, we will endogenize a number of firms, but for the moment, we assume that there are barriers to entry. And of course, as always in Cournot, aggregate output is just the sum of the individual outputs of summed over all individual output Qi of all firms I. And what we have here is a so-called simultaneous game, no two-stage game. That is, these firms choose R&D expenditure and output Q, R&D expenditure X and output Q at the same time, not sequentially. Later on in the chapter on research joint ventures, we will assume that they can choose them sequentially, and I think also in assignments there will be an assumption. But here for the minute, we just assume that they choose it simultaneously. That simply means that we get two first-order conditions. Okay, moving on. What is the optimization problem of the firms? Just checking whether it works. It should work. So it's standard here. We just have the profit of a firm I, and this is simply here's aggregate quantity in the inverse demand function. So it's simply price times quantity, revenue minus production cost minus R&D cost. And we take the, or we differentiate with respect to both output and quantity. Each firm does that in order to maximize, and we get these two first order conditions. The first one with respect to Q, the output, gives us standard marginal revenue. This would be marginal revenue, which has to be equal marginal cost. And the second one is even more interesting, because this is the condition with respect to the R&D expenditure. And so the interesting thing about this here is that these are, if you just think of the total cost we have here, total cost is simply Cx, oh, still be C times X here, of course, C of Xi times Qi plus Xi. And if you take the first, and if you minimize these costs by choosing Xi, the first order condition is exactly this here. So what you see is that our Cournot firms in this market just minimize their cost for a given output. And it's nice to interpret this first order condition. Just cheat a little bit here, put that on the other side. So we would get that here the left-hand side is equal to the right-hand side. The right-hand side is just 1. That means I have additional cost of €1 if I spend €1 more in terms of R&D. On the left-hand side, we have what does that bring in terms of profit gain. And the point is, if I spend more euro in terms of R&D, my costs go down, C prime, my operating costs go down. And if they go down by 10 cents and I sell, say, 100 units, I earn €10. So this was a good dollar spent. And I will spend so many additional dollar or euros until the two parts. I'm really cheating too much here. I just leave it like this. You know here, the first term has to be equal to the second. And so this is a straightforward condition, cost minimization condition. Now, what do we get here? Of course, we get n or n of these two conditions. So we have actually an equilibrium with 2n equations. However, everything is symmetric, so we simply look for symmetric equilibrium, and that just means that we end up with only two unknowns, and because we know the R&D expenditure X of each firm will be the same, and the output of each firm will also be the same. So we get two equations in two unknowns. What are we doing now? Employ the learner index and substitute the specific functional forms. So what we had, our equation 2 was nothing else than our first order condition, and what we have now is just we substitute our cost function, and this is now our equation. Here we have our 1, our additional cost, and on the right hand side on the left hand side you have these gain from the R&D expenditure, the reduction in cost. And so we can simplify or solve here for the R&D expenditure X. R&D expenditure X is just this here. And does that make sense? Naja, we just can look how R&D expenditure depends on output. You see Q. If you have a larger firm with more output, it will spend more in R&D, because a given cost reduction of, say, €1 is of course worth more when you produce 10,000 units than if you produce only 1,000 units. Additional alpha here, if you look up here to the cost function, alpha just gives you how productive R&D is. In a sense, it's an elasticity giving you an indication on how many % your operating, your marginal costs go down if you increase your R&D expenditure by 1%. And if this is a high value, of course, your R&D is very productive, and this gives you an incentive to invest more. The beta is another point here. Beta is also called parameter measuring technological opportunity. Why? This is a kind of strange terminology, but here you see the larger beta is, the higher the cost level is to begin with. But if you start up with a very high cost level, say 1,000 euro per unit, you have a high potential for reducing costs. Whereas if you start with a cost level of 10 euros per unit, you have a much lower potential to reduce cost. But anyway, so this is our result for the R&D expenditure here in the Dasgupta Stiglitz model. Next, we have to solve for the optimal output. Therefore, we use the learner index, and we could exactly go back here. You see whether I even noted something. This is a learner index we derived some hours ago, or some hours ago here. And you see the alpha is nothing else than the market share. Here we have n firms, so the n symmetric firms, so the market share of each firm is just 1 over n, and that's how we obtain our result here. Now I jump to the pen again. So here is just our result, and once we have this, we can simply solve for the price. We rearrange that, and of course, what is interesting in Cournot is not the optimal price, because we have to first substitute here the inverse demand function. So we substituted all these variables we had here. Our C we just produced a minute ago, okay, and on the previous slide actually. So here we derived the C of x, okay, and the optimal x, and that gives us this part here. This was our optimal x, and this is just substituted into this cost function here. And it's tedious, but after some manipulations you get the result, and that's why it's even though this result doesn't look very nice. And do I have a second one? Yes, where I expanded everything. It doesn't look nice, but it gives you many insights, and in a minute I will derive all the conclusions you get from this result. So we used a specific functional form, or actually Dasgupta Stiglitz used this specific functional form in order to derive the closed form solution. This is how such a solution is called, the closed form solution for the Q. Of course, once we have the Q, we can also immediately derive the R&D expenditure, which is the same, just substituting our Q we have here into this here. And if we substitute all that into the profit function, we get then the profit here also in closed form solution. And what I want to do now is I want to do some comparative statics, just to show you what kind of statements we can derive from this result. Actually, these statements are written on the next but one slide, but here I just want to illustrate them in terms of our diagram. So here we can produce really some comparative static results. So for instance, if you look into market size, what does an increase in market size mean? Actually, it means that Q increases. And if Q, sigma is only measuring once, and if Q increases, also X will increase. So if we have a given number of firms and the market size increases, we have a larger market, we will have larger firms, and each firm will invest more. What is also interesting here, the beta, if we have higher beta, what you will see is higher beta means higher cost to start with. So each firm will be smaller, because if costs are higher, the price will be higher and demand will be lower. And what you also will see, and that's what we also discussed here in this comparative static, what you will see in the next but one slide. I just show it to you here. I have these results here. The result I'm talking right now about is this here, and I'm going to demonstrate it. An increase in technological opportunities better decreases R&D expenditure if demand is elastic, that is, epsilon is greater than 1. That's what I want to show you right now, if I'm not again too impatient here. Yes, here we are. What you immediately see here, you have the minus epsilon. So if we increase beta, Q will go down. If we substitute the Q here, you get a beta here raised to the power of minus epsilon, and then you have this here. If you add this here, you will see it actually turns out that you get some equation where beta has in a numerator a 1 minus epsilon. And what you see here is if epsilon is larger than 1, that's exactly actually the statement we made is epsilon is larger than 1 if demand is elastic, and if, an increase in beta will lead to lower R&D expenditure. Okay, why is that so? Even though we have a positive direct effect, higher technological opportunity, the firm size is so small. Okay, I just need to check what further things I want to say there. Yes, the most important thing in a sense, but that's what I derive on the next slide anyway, is, and in terms of our discussion, in terms of Schumpeter, is what is the effect of a change in N? N is nothing else as a measure for concentration. The more firms we have, the less concentrated is the market. Okay, the less concentrated is the market. And so what we can do here, and it looks again ugly, we can look what happens if we increase N, what happens to Q. And you see this is an ugly expression. And here you can show, and this is again tedious, but hopefully you see you have it here, the N, and you have it up here as well. So what you actually can show that this equation is negative here if N is greater than 1 plus epsilon over epsilon. So actually if epsilon is 1 or greater, this expression is, so you could also rearrange that to write it as 1 over epsilon plus 1. This is easier, so you will see if epsilon is greater than 1, an N greater than 2, or or greater, actually N of 2 would be sufficient so that it's negative. So what does it mean? More firms mean if there are more firms active, each firm will be smaller. But if the firms are smaller, and I have to jump back again to the previous slide here, hopefully again not too impatient. If Q is smaller, also X will be smaller. Okay, and that's an important result here. If we have more firms, each firm will be smaller, and as a consequence, each firm will invest less in R&D. So that, in a sense, sounds bad, but actually it isn't as bad as it sounds, because we have more firms, and more firms means that even though Q decreases, the single output, N times Q might increase, and that's actually what happens. And N times X, the aggregate R&D expenditure, also increases. Final point here with N, I think we have some result with respect to pi. If, of course, as always, if you increase the number of firms, pi will decrease. That's what you see here in the very first place. If you increase N, this decreases, and this is not compensated for by the changes here and the changes here, because here we have a negative exponent which you might not see anyway. But here you see that typically we also have some assumptions on parameter, because this thing here must be positive, so we must not have too many firms active, otherwise our profit is just negative. Okay, so here is our results, once again summed up. An increase in N, that is a fall in the concentration rate, it reduces X and Q, the individual firms' output and the individual firms' R&D expenditures. However, it increases aggregate output, and aggregate R&D expenditure. This holds for this specific form, might not hold for all, but here it holds. An increase in market size, sigma increases R&D expenditure. An increase in technological opportunity decreases R&D expenditure. X if demand is elastic, that's what I also did. And that's another thing here. Profits are positively correlated with R&D expenditures in a cross-section of industries which differ only with respect to the above variables. So the point is, we saw that sigma will lead to higher R&D expenditure, but sigma also leads to higher profits. That's what you see on the what you could have seen on a previous slide. Actually, I could also, of course, show it to you. So here, hopefully, here you have the sigma. If you have a larger sigma, you will also have a higher profit. So if you compare two industries, where both industries are really identical apart from this market size, then the industry with the larger size will have both a higher R&D expenditures and higher profits. So that's what it means in terms of profits are correlated positively with R&D expenditures. However, that's no causality. It doesn't mean that these firms earn higher profits because they spend more on R&D, but they earn higher profits and spend more on R&D because market size is larger. Because this is a bit abstract and it's so hard to get a clear idea from these abstract formulas, I just gave you an illustration here where one is just for the monopoly case is just for your information. But what you see here, here's the number of firms, and we increase the number of firms from 1/2, the duopoly, up to 6 firms. And what you see, exactly what I saw and what somehow is Schumpeterian, R&D expenditure go down. However, if you see, I'm really bad at drawing this here. If I have to do it with a tablet which is not flat, and this is now a flat curve. Anyway, what you see is increasing n means lower x. It also means lower q. Okay, more firms. But what I get here, and I have to raise it, n times x increase. So aggregate R&D expenditure increase. However, here you see it rather clearly at a decreasing rate, and the same holds for the aggregate output. And of course, aggregate output is directly related to prices. So if you have more firms, prices will go down, but then at a decreasing rate. I now turn to the endogenous number case, but I make a short break here. Okay, back to our model. We had in the meantime a question on beta, what the variable or what the parameter beta means. In order to show you that, I just want to, if it works, just to show you again here the definition. So here you see beta, and here you have x. C of x is nothing else. That's something like the shape we had in some slides ago. Okay, and if you have here some beta 0 and a larger beta 1, this cost function will go up. And as these cost here, if you invest so much, suppose this is then 100 and this is 200, this is just the unit cost of production. So if you have a higher beta, your unit cost of production will be higher. Okay, that should be sufficient, hopefully, for the minute. Okay, then we move on with the case of an endogenous number of firms. So in the previous part, we assumed that there are barriers to entry and there is some given number of firms. Of course, that's not really satisfying, because somehow this number of firms has to be determined. And actually what we have here in terms of the x is nothing else, x is R&D expenditure, is nothing else as what we have here, some fixed costs. And fixed costs are nothing else than a barrier to entry. So what we can do is just so-called endogenize the number of firms. We know they need to invest in X. Just think of Tesla. They also invested or invest now in this factory next to Berlin, and they have to make rather high investment to enter here in that sense the German market or at all to enter the market. So you have to invest. So what we now assume is that we have a large number of potential firms, and these firms enter as long as profits are positive. And firms now simultaneously decide on three things, namely whether or not to enter, how much to spend on R&D, and how much to produce. And this is then rather straightforward given that what we derive by now, because the free entry condition is simply that we determine the number n star of equilibrium number of firms. It has to satisfy the condition that n star firms can break even, so they have a profit of 0 or greater, and n plus 1 firm could not enter. And typically we assume an approximate solution ignoring the integer constraint, where we just n calculate in a way that pi, the profit, is 0. Then we will get n is equal to 6.2, but of course we know we cannot have 6.2 firms being active. Then our solution would be simply 6 firms. 7th firm could not enter, as then the profits would be negative. Okay, but then it's straightforward to calculate the number of firms. Remember, now it helps that we derived already the profit. Okay, we derived already the profit. Here we derived the profit, and what you see, even though it's an ugly expression, again, the only thing we need is this expression up here, because if n makes this 0, pi is 0. Okay, and so you see we determine, actually, and we can do it immediately, put n on the other side. So n, the equilibrium number of firm, is equal to 1 plus alpha over alpha epsilon. And that's what we just, or what is written here, 1 plus alpha over alpha epsilon. But this is a really strange result. Why is that a really strange result? Because a number of firms, for instance, does not depend on market size. What does this mean? Irrespective of whether you are in the US or say in Denmark, you have the same number of firms being active. How can that be? Even though the market is much larger, how can firms nevertheless make no profits? Now, the solution here is rather simple and straightforward. Each firm now will invest much more in R&D, and therefore will have much higher cost, and each firm will have a much higher output. Each firm will be larger in the larger market. So n star does not depend on market size. It does also not depend on technological opportunities better, and that's the point I just explained to you. So we will have a larger firms in larger markets, for instance. Okay, that's what you just can immediately calculate, because we have these 1 plus alpha over alpha epsilon determines the number of firms, and then you jump back to our Q, substitute the n, you have a given n, and you increase the sigma, and what you see, if you increase the sigma, just your Q also increases. Okay, and if you increase the sigma and your Q increases, of course the R&D expenditure also increases. However, what is interesting to know is, do large firms invest or spend more on R&D than small firms? Of course, this is ridiculous to put it like this, because we saw that large firms spend more on R&D than small firms. But what is interesting, in percentage terms, do large firms spend more on R&D than small firms? So suppose large firm spend 10% of the revenue on R&D. Of course, that's much more than if a small firm spends 10% on R&D, but in a sense it's comparable. And what I'm showing you right now is, if we do some manipulations, which is actually straightforward, what you saw is that this here, this expression is nothing else than P minus C over P, which is nothing else than the learner index. And we can manipulate here a little bit more using the fact that, just to show you how economists solve such a problem or try to derive results here, you know that profit is just P times Q. Actually, I could put it different. It would be easier. P minus C times Q minus X. That would be our profit. We know that profits are 0. So what we can do is we can put, first of all, our X. Okay, you can look it up. On the other side, what we can do as well is we can here divide by n times. Did I want to derive? No, I wanted here. I just need to check. We multiply by n. We derive. We divide by p both sides. Okay. And what we also have here, the q is not nice here, so we divide by q here. Okay. We divide by q here, and then we multiply the right-hand side by n, or expand the right-hand side by n over n. So we get really n times x here, and p times q times n, which is q times n is just aggregate q. So we get really here on the right-hand side what we have here on the left-hand side, and here we have the learner index, which is identical to that. Okay, now I probably confused you again with my many lines, but what you see here on the right-hand side, you have some exogenous thing here, given that we have the parameters alpha and epsilon given. So this is the learner index, which determines this value. On the left-hand side, you have nothing else than in the numerator the aggregate R&D expenditure, and in the denominator you have aggregate R&D aggregate revenue of the industry. So this is nothing else than the share. This is the share of R&D expenditure, the percentage share. And of course you might again divide it by n. So here we on the right we just multiply it by n or expand it by n, and so you get the individual one. And this is the same for all firms. So very nice result. And of course, what is interesting here about this model, it produces, and I hope I have convinced you, it produces so many testable hypotheses. Here's a hypothesis that all firms will about exact, or even though it's large firms and small firms, all firms will produce about similar, or will have about in percentage terms similar R&D expenditures. Okay, and finally, n depends on the demand elasticity, because that determines somehow their margins they can make, and on alpha. In a sense, the R&D productivity, if that R&D productivity is a very large, if alpha is large, we will get, I have to check it, we will get a small number of firms. Okay, again, I think it's good if I show you a diagram. Hopefully, here I first again tell you the results which are already derived by means of the equations here. First, firms spend more in R&D on R&D in larger markets. That was the greater sigma I discussed, but spending relative to their size is the same. That's what I just derived. Industry spending on R&D as a share of industry sales is greater in more concentrated industries. That's what you see hopefully here as well. So here this is our share, and if n increases, this share becomes smaller, the left-hand side becomes smaller, or if n decreases, that is, if concentration increases, the left-hand side becomes larger. That's what we have here. Okay, so you always have to look onto your equations, and then you start interpreting that. That's what I typically then, or Max and I ask you then in the exam to also ask or to interpret your results a little bit. So the important point, however, this is not Schumpeter, because this is not a causal relationship here. Here we have more concentrated industries, but the reason why they are more concentrated is some exogenous variable, such as the demand elasticity or these alpha value, the R&D productivity, okay? And because both the number of firms and the R&D expenditure are determined simultaneously. And again, industries facing greater technological product opportunities, that's what I called here these R&D productivity, are more concentrated. That's what I just showed you a minute ago. Okay, and if innovative opportunities alpha are small, barriers to entry are small, and R&D expenditures are small. Okay, if you cannot do a lot of R&D, so you can also enter the market because no one will spend a lot on R&D, and therefore your fixed cost, your entry barriers will be low. Okay, so what I derived here was really many different, and what not I, but what Dasgupta Stiglitz already 40 years ago derived, was really many testable hypotheses on the relation between various parameters like market size, like technological opportunities, like demand elasticities, how they affect R&D expenditure, then also number of firms and output, and therefore prices and performance. So what we saw here, the problem is always a discussion of concentration. And that's what I alluded to in the very beginning when I mentioned this paper by Spalber, a recent paper in the Journal of Political Economy. Of course, it's always a Schumpeterian question, and it's asked now for a long time in the literature how that relation works. And actually what you see from these endogenous cases, it's not so clear what we expect anyway, because it's not a causal relationship anyway. So, therefore I had in your notes, which you hopefully have distributed with the slide deck I have distributed, economists have long considered these effects of the competitive pressure, but even though there was extensive empirical research, it's not clear-cut what the effect on this relationship between competition, which is typically proxied by concentration, and innovation is. There's also a quote by Sidak and Thies, and this states that despite 50 years of research, economists do not appear to have found much evidence that market concentration has a statistically significant impact on innovation. The point is, and that's what I write at the beginning here of my notes here, once you take into account other measures like our sigmas, our alphas and our betas, concentration does not explain much of the R&D activity because it's endogenous. Okay? And as always, as these equations are a little bit dry and hard to understand, I illustrated here what happens with respect to alpha and n. What you see is if alpha is small, if R&D is not very productive, you get a large number of firms because each firm will spend only very little on R&D, so entry barriers are low. But if alpha is high, you see here if alpha is too high, no longer two firms will be able to survive. Fixed costs are so high, like suppose in microprocessors you have to invest €1 billion or so in order to enter the market, and you have only a very small number of firms. On the other hand, here, if you have alpha, and here you have X R&D expenditure, you see that R&D expenditure almost explode if alpha increases the R&D expenditure. The R&D productivity. Okay, before I move on, I want to make here another break and ask for questions briefly. Okay, as there are no questions, I move on, and now after these tour de force through the Dasgupta Stiglitz model, you deserve some more like anecdotes and so on. And that's what I'm going to give you in the next, say, 10 or 15 minutes when I talk about patents and patent policy. What are patents and copyrights? These are intellectual property rights. What does this mean? They give you the ownership to an invention, to a new design or new creative work, and we will discuss in a minute in more detail what that is. And that means you get a temporary monopoly right. If you invented something, you have the property right and you're the only one who can use it. If one of the firms now trying to find a vaccine for Corona, it will get, for the coronavirus, for COVID-19, it will get awarded a patent, and then is a single one who is allowed to distribute that and also can set a price typically. Even though that will be a very interesting question, what price they are going to set. Now the point here, why is that important? Because this knowledge embodied, for instance, in this Weixen, has a characteristic of a public good. There are so many research laboratories which, once this Weixen is known, they could just analyze it and also produce it. So that means this knowledge is non-rival. Everyone can use it. And the question is, it would also not be excludable if there were no patent or no property right. So the property right, then the patent then helps the firm to exclude others from making use of its own knowledge. Even though the good thing about a patent is they have to also give this information to post this information to the patent office, so that everyone actually has this innovation and perhaps move on and develop a better vacancy or a cheaper vacancy or whatever. Okay. And the important point is, and that's what we are going to highlight later in more detail, it creates incentive to undertake R&D, because if you know you develop something which then, once you are successful, can be easily imitated by everyone else, so you don't make any profits because you can just charge a price equal marginal cost because you have so many rivals. No one would have ever an incentive to invest in R&D. Yeah, what are the key issues related to the patent system? Of course, typically protection is not perfect. What does that mean? You can invent around, for instance, or you can say that this is not really new and so on. So you get imitation, you get patent infringement, you get inventing around. That's how economists call that, to come up with a similar solution. And on the other hand, it's the problem here, you create a monopoly. A monopoly is not a good thing from the viewpoint of social welfare, because it goes line in line with deadweight loss, and it also produces or redistributes gains from consumers to firms in this case. However, the point is here, of course, there's a trade-off. If you don't have any monopoly right, you won't see much innovation. So what you have to trade off, the patent, the length of the patent, in order to give first incentives to innovate, and in order to also not to make these consumer surplus, the deadweight loss problem, too large. And another point is also optimal patent breadth. We will discuss that later, and I explain later what that means. And of course here, that's what we discussed already when we discussed the Gilbert-Newberry paper. You might abuse or misuse patents in order to limit competition, okay? We will also discuss that later on, once we look into how it empirically matters whether you have a patent or still have patent protection or not. And I first want to show you some empirics, how patent behavior really looks like. And in patents, of course, we have to talk about the offices who grant patents. In Germany, it's the Deutsches Patent- und Markenamt. On a European level, it's the European Patent Office. And in the US, it's the US Patent and Trademark Office. There is still no such thing like a real European patent. There was recently going some legal fights on, perhaps if you read it in a newspaper, just check it. And what are the different instruments to protect your intellectual properties? It's patents, it's utility models, it's trademarks, it's designs. In the notes, I give you some detailed description from actually the Austrian Patent Office, where you have a detailed description of what these things are. Patents are really technical things here, whereas such a utility model, or in German a Gebrauchsmuster, gets a lower patent protection. It's not really checked whether this is really new and something which is really innovative. In Germany it tells Neuerungen, die eine geringere erfinderische Leistung aufweisen. So these are innovations where innovative merit or innovative part is not very large, okay? And you also have trademarks, which of course you know, Coca-Cola and so on. You cannot simply put this trademark on your kind of black soda. And Geschmacksmuster is also similar. This is like design. If you have a certain car with a certain shape, you might also have a design. It's not a patent then, but it's a Geschmacksmuster. Okay, so somehow clear. Yeah, hopefully. Now some numbers, and there are some really nice pictures produced. I was too quick here. Produced by the European Patent Office here. Some trends in patenting here, and what the European Patent Office states, and I gave you the link in the slides, in the notes here, that Europe is a leading technology market, and you see that in 2017 you had more than 160,000 patent applications. I don't know whether you can read that, but anyway. So, and what is interesting here, on the upper right, you see the top technology fields. You see most important is medical technology, it's digital communication, it's computer technology, and it's electrical mechanical engineering, where you have the largest number of patent applications. What is also interesting is the firms which apply, and here you see in 2017 it was actually Huawei who had the most patent applications, just in front of Siemens, LG, and Samsung. And what you see here on the European level, Qualcomm is another company which you might be familiar with because they had a huge fight with Apple. They produce chips for smartphones. And the point here is what you see at the European level. You have the leading companies is a Chinese company, and then you have Korean companies, a US company, which applies for patents here, and Siemens is the second one. What is also interesting here, and this is an amazing slide, by the way, which is really produced by, of course, by European Patent Office. You see who applies. Is it large firms or is it small firms? You see 70%, 69% is large firms. A quarter is about small firms and individual inventors, and also universities and public research matters for somehow. What you also see here is the different countries. Here at the center, you have the different countries. You see mostly it's European countries, about half, and of that half, a third is about Germany, so 15% of total is Germany. Then comes France. Switzerland is important. You see Switzerland is part of the European Patent Office here, or at least of the it's accounted for Europe. Then a quarter of European patent applications is from US. A large part is also from Japan. China is important, and Korea. Okay, and here you see just the growth. I reproduced the same thing probably in your slides. You probably saw that for 2018, but this is pretty much the same, and numbers did not change much apart from the fact that Siemens overtook Huawei again. Okay, and that they put it slightly differently, and that the numbers, of course, are again a bit higher, 174,000. Okay, so here we saw 174,000 applications. Actually, I have here quite older number, and at that time it was only 113 in 2012. And you see, of course, you apply for a patent, but that does not necessarily mean that you also get one awarded. And here you see the three potential possibilities. About 50% of the applications end with a patent being awarded, but about 22%, or about more than 20%, stopped after search. What does this mean? Actually, that's my reading would be that the patent officer, the patent examiner, just looked into the literature, into the old patent applications and patent filings, and saw, oh, this innovation has already been patented, or in a similar way. Okay, and so here obviously these applicants didn't do their job well and didn't search for previous research. The others are then stopped during examination, and that would mean, okay, does it really work with this patent? Is it sufficiently new? Okay, the same thing does not exist, but it's almost the same thing as we previously had. So is a notch, which is a notch in an iPhone, is that the same thing if it's really actually hard edges? Do you remember? It has round edges. Okay, is that different if you have round rather than what is the opposite? So just really hard edges. Okay, is that patentable? So that's one of the questions a patent officer might have to deal with. Okay, so you got the idea hopefully, and then the next thing you again get, and this is slightly outdated, the top applicants. I already showed that to you. That's why I don't want to discuss it in more detail. But what you see here, if it works here, red on red is bad. It's about 2,200 or 300 patent applications each year from companies like Siemens or like Samsung and BASF. And you also hear these are more like Siemens, like tech companies. Here you see BASF here, BASF, a chemical company. LG should be clear. Robert Bosch is also interesting. Sony, also a tech company in a sense. Research in Motion, that was the former mobile phone company, and so on. And Huawei, you saw that they really caught up. This was in Europe, and here you see in US, and you see it's slightly different in US. More US companies are patenting, in particular IBM. However, Samsung from Korea is also important. Microsoft is here important, etc. The US system is slightly different. For instance, in US you can have a so-called software patent awarded. In Europe that would fall under copyright. And here you also see Google and Apple. That probably changed as well, but here Bosch and Siemens are also important patentees in the US. Interesting. So I already talked about China. China is always an interesting topic in the tech sector, not only there, but also in international trade. And what you see here is from a study of Philipp Böing and Elisabeth Müller, who formerly were with the ZEW. Elisabeth Müller is right now professor in Frankfurt, I think. And what they looked into was into patent applications. PCT stands for Patent Cooperation Treaty. That's somehow like an international patent. And what you see here, how this number of patent applications evolved over time. The top dog, in a sense, is the United States, and then you also have Japan doing a lot and Germany doing a lot. But what you see here is China. This would be China, okay? China really caught up. And the question is, what does this mean? Are they getting so good? So you see it's a huge increase from 2003 to only 10 years. They increase by almost 20,000 patent applications a year. Okay, so that's really amazing. Korea is a little bit more flat, or a little bit flatter. You have Samsung and LG here. But the question is, what is the reason, and what does this mean? And what Philipp Böing and Elisabeth Müller want to do, is want to look, all these patents, is this increase in Chinese patents a real one in a sense, or are these patents which are not as good as the other ones? And what they actually do is they measure the quality of the patents. How are they doing this? Yeah, actually, in a sense, a little bit how you measure the quality of a journal article or of an article. You would consider an article, even though there is a lot of discussion that, but an article which is never cited is perhaps not such a good article. And they do a similar thing here. They are so-called patent citations. If you file a new patent, you have to also state, in a sense, the literature. you have to state the patents your technology builds on. And what you see is that these Chinese patent applications achieved only 34% of the quality level of the other international PCT of the patent applications. Okay, and the important thing is you saw that the numbers are very much increasing, but the quality was decreasing over time. So in a sense, there was a government policy which said, okay, we want to have more patents, and then firms just do that. They churn out more patents, but as the quality of their research does not increase overnight and the quantity does not increase as well, they just churn out more patents, however, of a lower quality then. Okay. Patent quality of firms increases in R&D stocks, but decreases with the introduction of PCT subsidies. So the point is that's what you would expect if you get a subsidy as a company. If you file more patents at a patent treaty at a patent cooperation treaty, yeah, you will produce more patents. Okay, so if you get paid more for journal articles you write, you just write more papers. The problem is, and that's why we probably get these predatory journals, how well published are they and will they ever be cited? Okay, so what Boeing and Miller really conclude is that China's expansion of international filings was achieved to the detriment of quality. That's not saying that all these patents are bad, and certainly Huawei is very important, in particular in telecoms. That's what we already saw. German or companies have trouble rolling out their 5G if they 5G mobile telecommunications networks if they have to or if they are not allowed to use Huawei. Okay. Yeah. Patents are only one instrument to appropriate the returns from innovation. There are several other instruments if you have some innovation in order to appropriate the returns from R&D. Okay, so of course, for instance, Apple probably has superior sales and service efforts and is the first in a market with an innovation. And what Levin et al. Learned in a survey we did with I don't know several hundreds of R&D executives is that if they ask them which kind of method appropriating the benefits from innovation is effective and which one is not, they saw that being first with an innovation is much more effective than, for instance, patents. Okay, but you see in particular, and raise it again here, in terms of product innovation, patents are more important than for process innovations, and that's what you see here. Secrecy is also important, but that's in particular important for new process innovation. So if you're an innovative company with robots and innovative kind of production, you hardly ever will allow anyone to visit your factory. In particular, they are not allowed to take their smartphone with them. Okay, so the point here is that firms, first of all, patents are no perfect protection. Your new, even though you get a patent protection for something, it might nevertheless show up somewhere else by just some pirate who just didn't care for observing your patent. Okay, and you might also use just another instrument to learn that. I will get back to that again. Here is just a very nice example from a paper by Petra Moser. Here you see important instrument to appropriate the return from innovation. I don't know, maybe you know the golden delicious apple. This is such a green apple, a bit sweet, but okay. And obviously it was invented or produced. I don't know how you have these shots, how you do, how you produce this kind of trees, how you mix different trees and so on. Anyway, they produced it, and here you see how they prevented their intellectual property. Okay, that's really an interesting kind, and of course, in various ways this might still matter. You just try to prevent others from learning from your knowledge. Nevertheless, so the first message is patents are an instrument to protect your intellectual property, but other instruments are used as well. And the question is, how important are patents actually? And this importance differs a lot about different industries. And again, another study by Edwin Mansfield, asking also some R&D executives, and he asked what proportion of inventions would not have been developed without patent protection. And you see here, motor vehicles, we would nevertheless have cars if we would not have patents, okay? But in terms of pharmaceuticals, in terms of medical drugs, 60% of all drugs would not have been invented. Similar for chemicals and for petroleum, patent protection is very important. So what you see here in particular for pharmaceuticals, again, remember our case study on pharmaceuticals. Pharmaceuticals, patents are really important. Why is this so? Now, if you have a new, I think it's called NME, new molecular entity, each chemical laboratory can just, if you have a new ingredient, can just analyze it and also produce it, okay? So if you come up with something, some drug which treats something, if you don't have patent protection, you cannot somehow get back your research expenditures. What is interesting here is, I don't know whether you know about Tesla. Tesla has some kind of open source. I could look it up. Oh no, I cannot look it up because I lost it in a crash. Oh, I didn't. A closer look at Tesla has some kind an open source patent pledge. Okay, it has only about 340 patents, or had only about 340 patents in 2018. If you compare that with the previous number you learned, this is a small number anyway. Okay, but they pledged that it's open source, everyone can use it. However, it's based on reciprocity. But the point is, you see, in motor vehicles, it doesn't seem to be so important. Other things seem to be more important. Okay, just if you want to look that up, what Tesla does, and if you read something about that. Another point is, how important is patenting? This is a result from actually a working paper by Ashish Arora, Marco Cedianoli, and Wesley Cohen, which finally got published in 2008 without this nice table for whatever reason. But the interesting thing here is there a patent premium? So do you earn more due to patenting? And you have, of course, cost, and only if this value is greater than 1, the costs, or excuse me, the returns from patenting are higher than its cost. And you see, all inventions, it's 0.59. So for each euro you spend on patenting, you get only back 59 cents. So it doesn't make sense to patent all inventions. But however, for the all patent invention, this is better, because people or companies know whether it's useful to patent their inventions or not. And for the patented inventions, this is clearly not positive. Okay, for each euro you get €2.76 back. For biotech inventions, you see that all inventions are somehow in a positive territory, and the patented even earn more than €3. It's surprising that many of the semiconductor inventions have in a sense a negative return, because you get only back 31 cents per euro spent, because here it's mostly perhaps like production processes where it's much better to just keep this secret how you work it. But there are some inventions you patent, and here you see that from the patented ones you have a positive returns. Okay, so here I have, you see, and you hopefully it will become clearer later on why this story is so important here. This story about, do you patent or do you not patent? Do you use other instruments to protect your intellectual property. Because there's currently a huge discussion about whether we should have patent protection at all. But what you see here is, again, from a survey article by Brown, Win Hall, Christian Helmers, and others. And what they see is patent protection is more important for product innovation. Okay, if you compare product and process innovation, it's more important for innovations which have a longer expected commercial life. It's more important for innovations with, perhaps better use the text marker, for more innovations which have a higher value. It's more important for tangible parts of your innovation. You can do reverse engineering. Okay, intangible would be that's like knowledge only. Okay, you cannot reverse engineer intangible components. What you see here is research seems still undecided on how effective patent protection is. More competitors typically lead you to patent, and so these would be industry characteristics. And if your gap to your rival is small, you're more prone to patent rather than if you are really a leader who is much ahead. And firm size, that's a final thing I want to mention here. Large firms are very likely to patent, and small. So it's not the medium size, but the large firm, it's clear. You saw the Siemens, the Huaweis, the Samsungs, and so on. They have large R&D department with patent officers or patent lawyers and so on. The small firms, in particularly very small ones like the startup biotech firm, for them a patent is really important, because if you have a patent, you can go to your venture capitalist and show, okay, see, I have already a patent, so you really should give me money if you don't have any other these other complementary assets. And this is also just to put into perspective how important patenting is in the industries. And what you see is from all firms, more than 85 or about 85 or more percent doesn't use any of these mechanisms to protect your intellectual property. But there are some firms for which is very important, and in particular for the firms which you would consider high-tech firms which do R&D, about a quarter and more say that it's very important to them. Okay, so there's no one size fits all. You cannot say patents are not important, because I know these automotive producer who says, oh, no problem. The point is, for some it's very important, for others it doesn't matter. But if you would say no patents, that would mean hardly any pharmaceutical innovation, for instance. Yeah, that's why I discussed it so much. There's a famous paper by Michele Baldwin and David Levine against intellectual monopoly. So they are outright opponents to intellectual monopoly and to patents. And they are consequent in a sense, because they don't want to have the copyright in a sense. Even though you can buy this book, you can also download it. And I gave you the link to the book in the notes. Another book which is very interesting and important is a book by Adam Jeffy and Josh Lerner, Innovation and its Discontents. And that's really worrying what they state, because they show how strange the American system, patenting system, really works. And typically I gave you one of the examples we have. It's the example of the sealed crustless sandwich, which got a patent awarded. Just to put it in German terms here, this is like a Hesse butcher would get awarded a patent for a Fleischkäsesemmel, even though this is sold for centuries in Bavaria as a Leberkäsesemmel. I have to apologize. I cannot translate Leberkässemmel into English, but if you ever manage to go to Bavaria and you're not vegetarian, just order Leberkässemmel with süßer Senf. But the point here is, in the US, you get patents awarded for things which are clearly not worth to get a patent, and you get a lot patent litigation as well, and that's what I have on the next slide. This is what is a patent troll. You have non-practicing entities, better known as patent trolls. These are actually, these are not no firms. These are actually one inventor who invented once or twice, or who has one or two patents, and these patents for some reason ended up in an iPhone or something like that, was used there, and now they litigate, and they have so there's this patent lawyer then, and they start to litigate. They file a case against the different companies, and they produce huge costs here in terms of 500 billion. So here you really have a problem, and I gave you some more information in the notes. The point is here not that these inventors do not deserve to be refunded or remunerated, or to get some payment for their knowledge and for their invention, but they probably would have never made any money from doing something, producing something on their own. Okay, and of course then charging, say, or demanding, say, $10 per iPhone, yeah, you see, you would make really a lot of money. Okay, actually, so this was in a sense the story I wanted to tell you, to give you some idea what patents are, why they are important. They are of different importance. They are of different importance for different industries. Actually, we could jump back to our most important fields of technology in terms of patent applications. You saw there it's communications, it's also chemical industries. You don't see pharmaceuticals there, because in pharmaceutical industries you only have, say, a few inventions each year, but these are very important inventions typically. So if you have now an invention providing a vaccine for corona, you know that this would be worth billions of euro for our economies. And of course, the first question is then, or if you are clear then, or if it's clear to you that you want to have a patent, the question is, how long should it be valid? And here again, we jump back to the very beginning. So we have a basic trade-off here. If you don't have patent protection, no one will undertake R&D. You see, automotive producer will undertake R&D, but pharmaceutical company might not. Okay, so you need some R&D incentive, and that is, you need some monopoly power. But at the same time, monopoly power means that you have lost due to monopoly power in terms of consumer surplus, and you have to trade off. So what is the optimal extent of patent protection? How many years should you have? Actually, by the way, do you know how long a patent, how long, what the validity of a patent is, or a patent length? I should have asked you earlier, but it's written here anyway. So in the EU it's 20 years, in the US it's now also 20 years, in the UK it's similar. And this slide shows you how important patent protection is in the pharmaceutical industries. Here you see Pfizer and Sanofi and BMS. Sanofi is a European company, formerly, or Höchst became part of Sanofi at some time. And what you see here is, if patent protection expires, which was the case here in 2011 for Lipitor from Pfizer, which is a cholesterol lowering drug, you see revenues decreased by 6 billion. Okay, so you see half a year or 1 year is worth a lot. Okay, and with here again 5 billion did revenue go down. So here you see why it's so important how long this patent is, and of course what happened to the prices, they also collapsed. So our Krankenkassen, our health statutory health system had to pay less. Okay, they had to pay much less then. So this is the other side here. Okay, and So what I cannot show you right now because I'm running out of time is the nice model by Wilhelm Nordhaus, who received the Nobel Prize, I don't know, in 2017 or 2016, actually for his work on, mainly on his work on the climate change and the greenhouse effect. But he had a very famous paper on the optimal pattern length where he looked into the trade-off, okay? And again, the trade-off is, and I will jump back to that later, is simply what we have here, okay? On the one hand, we have, this is just from the arrow model, okay? This is your gain from innovation, which depends, which you get as long if you have invested so much X, if you have reduced your cost so much, you gain once you have competition. And on the other hand, so this will turn out to be your gain from innovation, your incentive to innovate. On the other hand, you have this dead weight loss. But here, I think I just should stop and move on. At this point, say in a week, I apologize for the technical problems we had today. Hopefully it nevertheless was okay. And I will be available on WebEx right now for further questions, and thank you for joining me. Goodbye.